Hi, it is me again. Sorry, it's not fixed. Hi again, it is me. Today we will continue our topic on gas turbine. Okay, this is the quiz that I gave to students of last semester, not last semester, last year. If you read through the question there, let me read for you. A gas turbine unit draws in air from atmospheric pressure at 100 kPa and 10 degrees Celsius and compress it to 500 kPa with isentropic efficiency of 80%. The air is heated to 1200 Kelvin. Please see this in degrees Celsius and this one in Kelvin. Okay, and the air expanded through two stages of series back to 100 kPa. Okay, the pressure turbine is connected to the compressor and produce just enough power to drive it. Okay, and the low pressure stage is connected to external load and produce 80 kilowatt of power. The isentropic efficiency for both is 80% at the stage of expansion. Okay, and calculate the mass flow rate or m dot of the air in the cycle, the intermediate stage pressure of the turbine in kilopascal, and the thermal efficiency of the cycle. Given that the lambda for compressor is 1.4 while the lambda for turbine is 1.33 and the gas constant is given as R. This is R. Okay, so the first step again for this solution is to list up. Okay, to list up every single important information inside this question. Let me write up for you. Where's my pen? Big one. First one is given T atmospheric or T1 is 100 kPa kilopascal. No, this is P1 not T1 because P stands for pressure, T stands for temperature. So the T1 where P1 as 100 kPa and the T1 is 10 degrees Celsius equivalent to 273 Kelvin, 283 Kelvin, right? Kelvin. Then P2 500 kPa, and isentropic efficiency of the compressor is 0.8. Okay, the air is heated at 1200 Kelvin, which is T3. T3 is 1200 Kelvin. And is expanded through turbine in series, okay, to 100 kilopascal. The external load produce 80 kilowatt power. P net given 80 kilowatt power. Expansion of the turbine, the efficiency is 0.85. Find the m dot the temperature x, let me put it as x, and the thermal efficiency. Good. Solution, change it to red. Solution. It is raining outside, so the first thing first, if you want to solve this kind of question, you need to read thoroughly. Okay, read thoroughly the question back and try to draw it in TS diagram. Okay, read thoroughly multiple times and try to sketch it in TS diagram. Good. So from my understanding, and also from the information given here, there's one compressor and two turbine. So let's say like this. This is your pressure line. Okay, this is P1, this is P2. Good. So this is where your temperature 1 came from. This is where your temperature 1 came from, T1. Whereas your T1 is 28K, right? So it goes to, it compressed by a certain pressure, not certain pressure, this is 500 kilopascal, it isentropically. So what is your T2? It's not given here, but you can find it using equation. Okay, and it is expand again through P2 in 500 kilopascal to the maximum temperature of, let's say here, this is your T max, 1200 K. After that, if you read carefully the question, it say that your compressor, or sorry, your turbine has a two stage which is connecting in series. Okay, so it is supposedly like this. Yes, so this is your first stage, and this is your actual temperature. So basically, let me write through again. This in row, this is T2, this is T1, and this is T3, and this is T4. We want this this is T3, this is T4, this is T4A, this is T5, this is T5A. Okay, you have value here for T2A. T2A. There. Okay, good. The question giving you this line pressure 100 kilopascal. and this line pressure is 500 kilopascal. But they don't give you any number for this Px, and also Tx is actually T4A here. We want to find it. Okay, so what do you need to do is, first you have to rewrite the formula again. This is the basic formula where you can find that T2 or T2S divided by T1 equal to P2 over P1 with lambda minus 1 and lambda. You can find the T2S, T1, P2 over P1, lambda minus 1 and lambda. What is your T2S? T1 is 283, right? It is raining outside. Hope you can hear me. And this is 500 divided by 100, and your lambda is 1.4 minus 1 divided by 1.4. Then your T2S is 448.21 Kelvin. This is your T2S. Okay, T2S. So what is your T2A? We need to whatever important inside all this temperature is actually the actual one, not the isentropic temperature inside the graph. Okay, inside the diagram you need to find the actual one, so then you can find the work in, the work out of what you needed. Okay, because in the formula we always using the actual temperature. Okay, so for T2A you can find it using compressor efficiency equal to T2S minus T1 divided by T2A minus T1, and you rearrange it back. T2A T1 plus T2S minus T1 divided by, yes, okay, from that you can find the T2A. And the plus T2S 448.21 minus 283 divided by your efficiency. What is your efficiency? 0.8. So your T2A is actually 489.51 Kelvin. So you got T2A. Okay. Next, you need to find a T4A. You know that you can use this basic formula. Okay, by writing like this. I'm using a purple. T4A, not T4A. T3 divided by T4A equal to P2 over Px lambda minus 1 divided by lambda. So when we rearrange this equation, you can find the T4, right? Because we need the T4. However, look closely. We don't know the pressure of Px here. We don't know the pressure of Px here because it's not given. The information is not there, and when we draw the TS diagram, it appears Px is non-value there. So we cannot solve through this equation. I repeat, we cannot solve through this equation. Indeed, we can solve if we have a Px value, but in this case we don't have a Px value. So what we have to do, we read back in the question. We read back in the question. Here, this is the important part. The high pressure turbine is connected to the compressor and produce just enough power to drive it. What does it mean? It is mean here the work in here, this is work in, is equal to work out here. Okay, work in there is equal to work out there. So what you can do here is just delete all this. Let's do a quick delete. Okay, we know that work output for this, for a compressor, is work in equal to Cp times the bigger temperature minus smaller temperature. Okay, for this one is actually your work out for high turbine equal to Cp times T3 bigger temperature minus smaller temperature T4A. So when the question tell you that the work out, also the work in here is just enough to drive the turbine here. So which means that work in equal to work out. So you can equate this equation by using Cp, not using it. There's no trick here. Okay, there's no trick. T2A minus T1 equal to Cp T3 minus T4. Okay, Cp here using 1.005 and Cp for here using 1.15. So you can find the T4. T2A you already calculated. This is your T2A, and T1 here given inside the question. This is your T1 28K. The T3 also given inside the question, which is 1200 Kelvin, and you can rearrange back. You can get a T4A. In my answer scheme here, your T4A is supposedly to be 1019.53 Kelvin. Okay, there you go. So you already have a T4A here. This is your T4A. Basically, you already answered this. You already answered this. Okay. And next, you need to find all this temperature: T4A, T4, T5, and T5A. Okay. So what is your T4S? How to find the T4S? Using turbine efficiency. This is turbine efficiency. So turbine efficiency equal to T3 minus T4 A, T3 minus T4S. You need to find T4S. Okay. You don't have to memorize all this number. When you look at the turbine for this, you want to find T4 right here. So you have to know this is the turbine side. When turbine side, the isentropic temperature is always at the bottom, denominator. Okay. So you have to minus bigger temperature minus a smaller temperature first, and next bigger temperature minus smaller temperature, but in the S at the bottom. Okay, so you can rearrange back and make the T4S as your main functions. Then you can have, this is just put it here. You got the T3, you already got the T4. You can find the T4S. So for my answer scheme, your T4S supposedly to be 987.68 K. Okay. And next, you can solve easily. You can solve easily this question because you already have the temperature here. You already have a temperature here. When you have a temperature, you can use back the pressure equation just now. I already write it for you. The pressure temperature for this one, T3 over T4S equal to P3 divided by Px or P4, lambda minus 1 lambda. There, this Px. So you can rearrange this. You can rearrange this equation to get the what is your Px. So P3 over Px equal to T3 divided by T4S lambda divided by lambda minus 1. So your P3 Px equal to 2.19. Okay, so you got 2.19. the ratio of P2 over Px. So how to find a Px? How to find a Px? Exactly, you can use the change rule instead, where you know that P2 over P1 equal to P3 over Px times Px divided by P1, right? You can delete it where P3 is equal to P2, then P1 is P1. Okay, so P3 and Px you already have this P2 and P1 you already have at the first place. The question giving to you 5. This is 500 divided by 100. This is, for this one is 2.19. And how about this one? It's simply 5 divided 2.19 equal to Px minus P1. So when you got this Px over P1, you can solve for T5 here. How? Let me show you. T4 T4a divided by T5 equal to the ratio of this Px over P1 lambda minus 1 and lambda. So your T5, what is your T5? T4 you already calculated, Px, P1 you already know this one, and lambda minus 1, lambda using 1.15, not 1, sorry, 1.11 if I'm not mistaken, sorry, 1.33, this 1.33, this also 1.33. If you plug in all the numbers there, you can get the T5 8, it's not 8, this is 831.59 Kelvin. Okay, and what is your TA? How to find your TA? Same, using efficiency of turbine, which is T4a minus T5a, T4a, T5s. Why you need to find T5s here? Do you need that? No, I'm sorry, I do feel sorry. No, it's correct, In this case, you need to find T5A, sorry. You need to find T5A. The efficiency turbine using this. Where is your turbine? Is using this 0.85 T4. Where is your T4? This is your T4. You already calculated. This is your T4. 119, what is the point? 0.53 minus T5A. Let me go down there. 119.53 minus T5, 831.59. So you got the T5A. What is your T5A here? 798.42 Kelvin. This is your T5A. After you got all the temperature, then you can calculate all the work net, the power output and everything. So here the question, still you haven't answered two of what you need to find: the m dot and the thermal efficiency. The m dot here you can find from power output. Given your power output, right? The power output equal to, what is the power output given to you? If I'm not mistaken, it is 80 kilowatt. 80 kilowatt here. 80 kilowatt. So your power output is 80 kilowatt. We know that power output equal to m dot times work net. Whereas your work net equal to Cp times, look at your TS diagram. This is your work net, T4, the bigger temperature, minus T5A. This is your temperature, T4A minus T5A. So you can have a positive work net instead of T5A minus T4A. So if you use that equation, you will have a negative work net. It is very wrong. Okay, T4A minus T5A. So use Cp here 1.15. So your T4A, you already calculated and everything. So supposedly your work net is 254.27 kilojoule over kg. Good. Okay, thus you got the work net. Then how to find the m dot? M dot, this equation. So P out divided by work net. Your P out is 80 divided to 54.27 power of 3. M dot is 0.314 kilojoule over kg. Good. So this is your work net. No work net, the mass flow rate. The mass flow rate of your system. So the last one, you need The question asks you to find the thermal efficiency. The question asks you to find the thermal efficiency. So how do you do that? You know that thermal efficiency equal to work net divided by heat Q in. Okay, where's your Q in TS diagram? Your Q in, sorry, this is your Q in. This is your Q in right here. This is your Q in. Okay, so how to calculate it? Q in equal to Cp, bigger temperature minus smaller temperature here, T2A. Okay, so you have a T3 minus T2A. You already calculate the work net. Where is your work net? This is your work net. Just write it back to 54.27 divided by Cp times T4, not T4, T3 minus T2A. It's all there because T3 is given. Yeah. T2A also you already calculated, so it's all there. After that, after all this, you can press your calculator, then you will get 31.11%. Use Cp 1.15. How do you know? How do I know where to use Cp for 1.15 or 1.005? How do I know that? It is through the question. Okay, this side is always turbine. This side is always compressor. When the compressor, if you look closely at the question, when it's compressor part, the Cp is always 1.005 and the lambda is 1.4. In the turbine side, the Cp always 1.15 and the lambda use 1.33. Okay, 1.33. It is depend. Okay, sometimes the question giving you 1.0. Just follow the question. Okay, but basically like this. It's always like this. So hope there is no question. If you want the question, it is here. This is the question. You can snap through your phone or something else, or print screen, whatever device or do you use, so you can connect it, or you want me to email you also, no problem, as long as you do some exercise there. If you do some exercise, you will get what you are doing. Okay, that's it. We will have another last tutorial for gas turbine. That one from last year final year question, and very past year final year question. Okay, we will do that for gas turbine. I think there is 2 there. We will only do it for 1 question. Okay, hope that it will help you for incoming examination. Thank you for today. Hope it is help. Okay, thank you again.